Welcome to another episode of QuaranTIME. We are live. And if it is your first time tuning in, this is a show that we make for parents of kids age 7 to 12. Kids age 7 to 12, that's our main audience, but we hope it will be something that the whole family will enjoy watching. And we also know that we are reaching some viewers who are feeling isolated because they are home alone because of the quarantine measures. They're over the age of 70. They're not able to get out and interact with other people. And they really enjoy seeing the chat and all of the interaction that happens on our show. So welcome to you, whoever you are, wherever you're watching. And in the chat, I'm seeing responses to the question that we asked of where are you watching from all over the United States. So welcome to Francie, Izzy.
Minnesota, West Virginia.
Yes, so many different places.
Pennsylvania, New York.
We are super happy to have you here, and we are excited to share another episode of QuaranTIME with you. I'm Science Mom, this is Math Dad, and today we are going to be covering some incredible chemistry. I feel like there was something else that I wanted to say right at the beginning. Do you remember when we were talking beforehand?
Was it related to the art prompt? Oh,
art
no.
Prompt?
No.
No, it has left my mind.
We're getting
I'm not
old.
Sure.
Getting old.
We are. So we have a format that we like to follow where we share at the beginning of our show, we share the artwork that was done on the previous show. And last time we forgot to actually give you the art prompt, but enough of you have been watching regularly that you knew where to find it. And we got some fantastic submissions. Yesterday's art prompt was to do single line drawing. And I have to say, it is pretty tough to draw with a single line. Come over to this side, Math Dad. And so they could still see you, and take a look at this. So I love what Ava did because she did a cat without lifting her marker from the paper, all in one single line. And then she did one with lifting the marker, thinking like a scientist, trying it both ways. And you can see that it's challenging to do when you don't lift your pen, because then all your lines need to be connected. You can't have the nose up in the middle of the face. You can't have the eyes, separate. Every line needs to be connected. And this is challenging. We got fantastic submissions of single line artwork. There's another cat. Isn't it cute?
Yep.
And now I'm going to share my screen with you, and we will go through and show you some of the artwork that we had. So here we go. I hit share, and you get that nice like infinity window going on forever until we pull up our slideshow and hit play. So we have a person walking a dog and a beautiful flower where you can see that they carefully kept their pen connected the whole time. A house. We got some beautiful landscapes.
So do you know what this reminds me of? The Etch-a-Sketch?
Oh, it is kind of like Etch-a-Sketch.
Etch-a-Sketch, you were never allowed to lift your... I mean, it was one continuous line the whole time, so you had to be clever about it.
Could you do this on an Etch-a-Sketch?
It no longer reminds me of an Etch-a-Sketch. This is awesome.
Nice job on this one, Addie. And then we loved this, after you did your drawing, you could color it however you wanted. I loved the sort of like the telescoping view here. This horse was fantastic, nicely done. Cloud and a sun, a Miss Rainbow with her pet, an octopus. This was the first one that came in, and I thought it was fabulous. This one reminded Venora, sorry if I say your name wrong, of a tortoise. It reminds me of a tropical fish. Don't you think that looks a bit like a fish?
Yeah.
And then we've got a fire-breathing dragon. Awesome job here, Gavin. I thought that one was great. Cute little cup. Isn't that cute? I love that one.
Happy Coco.
And that looks like a phone to me. Nicely done. Good job, Paige. A doggy plant. Isn't that great?
That is great.
Very nice. And it is all connected. And I thought this dog in the bubbles was very, very fun. Darth Vader and an elephant. Loved these. The elephant in particular. That's really tricky to do. And I thought they did a great job of making all the loops look like part of the elephant. And I love Darth Vader too. A hummingbird with a flower. Aren't you impressed with this artwork? I got to tell you guys, Math Dad is looking at this, and I can see him being like, all right, I'm going to practice drawing. I'm going to improve my skills.
Well, when they can draw better without lifting their pencil, then I can draw when I can lift my pencil. Yeah, I'm a little jealous.
I really loved seeing all of these. We've got an ice cream cone, cute little puppy queen. And we'll pause here and we'll share some more later on in the show. But thank you to everyone who submitted their artwork. We really enjoyed seeing all of the fantastic art creations you've done. And for those who are not sure where to share, let me show you real fast, because Math Dad and I, we have enough, it's a lot of work just to get ready for the next show. So we're having Science Mom Krista. She's the one who is going through and selecting the drawings. So shout out and big thank you to Science Mom Krista. And the way that you can submit yours is to go to Facebook. And on Facebook, you'll see this album that we made. And then if you click on the album, then just click the whichever prompt for the engineering challenge or the art one is there. And then in the comment, you can put your picture there. You can also post it to Instagram. Science Mom Krista will check Instagram for the hashtag Science Mom Squad, and she'll pull artwork from there as well. And of course, if you want to email it to us, you can, but Science Mom Krista does not check our email as often as she does Instagram and Facebook. So best chances are to put it on Instagram and Facebook. But thank you again to everyone who shared the art. We really enjoyed seeing the single line drawings.
I'm impressed. I must have wasted my youth. I didn't get the art gene.
Didn't get the art, but you got the math.
Okay, there we go.
Yeah,
I did something with me.
Now it's time for the chemistry lesson. You guys, I'm so excited to share more chemistry with you. Quick review of what we learned yesterday about atoms. So people used to think that atoms were just these little solid bits, like the smallest bit of something that you could find. So if you had something like gold, they knew that gold was a pure element. You couldn't take gold and change it into other things very easily. The smallest bit of gold that was still gold would be an atom. But it didn't take long before we discovered, hey, there are charged particles in these atoms. Say hello to the negative electrons. So then our theory was that negative electrons were floating around in the atom, sort of like raisins in a plum pudding. And of course, then the orange part of the atom that I have drawn in this little picture would be positively charged. Well, that theory didn't hold up for too many years, because then we discovered that atoms had a nucleus. All of the mass in the atom was in the center, which means most of an atom is actually empty space. This one still is kind of mind-boggling to me, really cool to think about. And then our negatively charged electrons orbiting around the outside like a planet. That theory held up for just a few years until we discovered that, hey, electrons have different amounts of energy, and the electrons that are on the inside of the atom behave really differently than the electrons on the outside of the atom. Chemistry is sometimes called the central science, and the thing I love about chemistry the most is that so many answers to our questions can be found in the chemistry. If you have ever wondered, like let's say you have a balloon of helium and a balloon of hydrogen, both of these balloons are going to float. They're going to be very light, and the gases are going to behave really similarly in terms of how light they are. So balloon of helium, balloon of hydrogen, they'll both float. But if you pop them on a candle, the helium one is just going to pop, and the hydrogen one, I did that backwards. Let's try that again. If you pop them on a candle, the helium one will just pop, but the hydrogen one will turn into a huge fireball for a few seconds as all of that hydrogen ignites. And the answer to why that happens is in the chemistry. So let's take a little closer look at an atom and what an atom is with the example of helium. So an atom has a nucleus, and inside the nucleus, you have protons and neutrons. And if you were to weigh an atom and say, how much does an atom weigh? It's all here. All of the weight of the atom is with these protons and neutrons. The protons are positively charged, the neutrons are neutral, and then our electrons orbiting around the nucleus, they have a negative charge. So this is helium, and all of these are hydrogen. So it doesn't matter if you have one proton and no electrons, or if you have one proton and one neutron, or one proton and two neutrons. All of these are hydrogen, because the proton, how many protons you have, that tells you what element it is. And hydrogen has just one proton. But if you bump up to two protons, then you don't have hydrogen anymore. Now you have helium. We call different types of elements that are the same element but have different weights, because obviously this one here, this is going to be way heavier than hydrogen. Most times when we're talking about hydrogen, we're talking about this type here. That's the hydrogen that we know and love that makes up 99% of our universe and is the most abundant element. Maybe someone fact check me on the 99%. That sounds really high. Most of our universe is hydrogen. I don't know the percentage. This one, deuterium, is a lot more rare, but we can find it. And you can actually get heavy water that's made out of H2O, where the H is deuterium instead of hydrogen. And then this one is a lot more unstable and doesn't last for very long. But every single element will have different isotopes where you can change the number of neutrons and you get something that behaves differently but is still that element. Now, if only there were a way for us to see all of the elements, because we know that helium and hydrogen are really different from each other. But what about if you have 3 protons? Because every time you add a new proton, you get a new element. What if you have 5 protons or 105? Well, dun da da da. We have we have a periodic table of elements, and let's see if Math Dad and I can get this down without it. Here, if you look at the top one, it should just roll. There we go. Woohoo! And now I got to adjust our view just a little bit. There we go. You can almost see the whole thing. Ta-da! This is the periodic table of elements. And over here, we have hydrogen. And then as you go across, you just keep increasing the number of protons by 1. So helium, and then you come back here. Lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. And the cool thing about the periodic table of elements is that if you're going across, you're just increasing the number of protons by 1. But if you look at the columns, you start to see patterns. And this is really pretty amazing. So everything over here in this column, super reactive. And it all has to do with the electrons that are around that nucleus and what they want to do. So hydrogen only has 1 electron. Turns out electrons really want to be in pairs. And so for that hydrogen atom, it's like, oh, I only have 1. I need to find another one. I want to either give it away or I want to bond with something else. Helium, on the other hand, over here, the noble gases make up this column. They're super stable because they have a full ring of electrons. And so they're like, why would I bond with anybody? I'm happy by myself. That's our noble gases. You looked like you're about to say something.
So I noticed there was a question last time about silicon.
Oh, yes. And I was going to look that up, but you did.
I looked this up. Okay, so silicon is sitting here. It's element number 14. And the question was, what's the difference between silicon and silicone? And yeah, so silicon is actually an element itself. And when you talk about like silica particles, we're talking like sand, it gets made up into the glass, say. But then silicone is synthetic. So it's like you use it for like caulking on your windows. It's so some rubbery like substance. So it is made of some silicon is one of the ingredients, but it's not the pure ingredient. Like is silicone just pure silicon? I don't think it is. I think there's a lot of other stuff in there. I didn't look up a recipe or I'm not sure of the exact composition, but
we will have more on that soon. So that is a quick introduction to our periodic table of elements. And now I want to do a quick little experiment. I'm gonna ask Math Dad to help me with this. So this is a plastic bag which has had a good life, has been used several times, and we are now going to pour some vinegar in it. I've got a container of vinegar right here. Vinegar is mostly water, but there is an acid, a weak acid inside the vinegar called acetic acid. And so we've got vinegar in our bag now, and then in this Kleenex tissue right here, I have baking soda. And I'm going to carefully put this baking soda packet into my bag.
Why are you doing that so carefully? Shit. Wait, what's?
Okay, so this is our segue into talking about chemical reactions. This is our kind of our main topic of today. So we did a quick review of atoms, introduced the periodic table, and now we're going to talk about chemical reactions. So I'll hold this a little closer so you can see it a little bit better. We have a bag, and this bag is fairly flat. It's sealed, most of the air is out, and we have a packet of baking soda up here, and we have vinegar down here. So do you know, tell me in the chat if you know, what's going to happen when these two mix? If we have vinegar and baking soda, what are we going to get? And it is just white vinegar. You can use anything. And now Math Dad, come over here so they can see you. I'm going to hand this to Math Dad. You've got to shake it and then just hold it. And you can see he's got a should
I be scared here?
He's got a bucket here because I told him he might want it.
Okay. Okay.
That's good.
My favorite type of bath. Vinegar.
Now, I should say vinegar, 5% vinegar, what we were using is pretty safe, but it would have been a really good idea if I'd had Math Dad wear safety goggles for this, because anytime that you're dealing with something that could splash, you should have on safety goggles so that you don't get it in your eyes. Math Dad's glasses kind of count as safety goggles, but if I were being really good about being safe and protecting Math Dad, I would have given him safety goggles. So my apologies, Math Dad, that we did not do safety goggles before. But the reason that the bag popped is because we had a chemical reaction. So let's turn over toward our whiteboard and we'll talk a little bit more about chemical reactions before we do our next experiment. So here we go. And you can see our notes from yesterday. I'll erase those real fast. Now, when you have a chemical reaction, you have something new formed. When you have a physical reaction, you don't have a new product formed. You have the same ingredients that you had at the beginning, you still have at the end, but they might have changed state, they might have changed the way that they're interacting with each other a little bit, but you didn't form something new. So when we react vinegar and baking soda together, we get a gas, we get bubbles. And that gas is carbon dioxide, which you might remember from last week when we talked about dry ice. We talked a bit about carbon dioxide. So we have a chemical reaction here. Baking soda plus vinegar equals carbon dioxide. Now, chemical reactions happen all the time. That's why we're alive, because we have chemical reactions running in our cells to get the energy in the food, to convert that to carbon dioxide, and to give us energy so that we can build things in our cells. We are actually kind of, you can almost think of the human body as like a giant machine with all sorts of really complex chemical reactions happening all at the same time. So vinegar plus baking soda gives us carbon dioxide, and the vinegar changes. So our baking soda becomes part of the carbon dioxide, the vinegar changes as well, and we end up with different products over here. Instead of acetic acid, the main component in vinegar, we end up with, I should have looked this up before I did it. I think it's, on live TV, sometimes it's really hard to remember what you were going to say. I'll have to look it up for you later. But here is the reaction that we just did. Now, the second experiment we're going to do is a little bit different, and it's called salting out. And I'm going to turn around here, and then I want you guys to tell me if you think this is a chemical reaction or not. So here's how it works. It's pretty simple. We are going to take a jar, and into this jar, we are going to pour salt. A couple spoonfuls of salt. How much exactly doesn't matter too much. And once you have your salt in your jar, then you're going to add rubbing alcohol. And the cool thing about what we're doing here is that you can actually change the concentration of rubbing alcohol. So let's say that you went to the store because you were almost out of rubbing alcohol, and what you really needed was a concentrated form of alcohol. You wanted 91% rubbing alcohol, but the store was all out of this type of rubbing alcohol. They didn't have it at all, thanks to panic buying and whatnot. And the only type of rubbing alcohol they had was 50% alcohol. Could you change your 50% alcohol into a more concentrated form of rubbing alcohol? It turns out that you can if you just add salt.
What?
Yes. Get ready to be amazed, Math Dad. So we are going to take our container with some salt in it. We are going to pour in the rubbing alcohol, and we need to get it about, again, measurements aren't super, super important, but you want to have a little layer of salt, half full of rubbing alcohol. That's pretty good. And then we're going to put a lid on it and shake it like crazy. Math Dad's like, shake it higher. They can't see you. So we shake it really well, shake it really well, shake it really well. And then we need to wait for about 15 minutes to a half hour. So I'm going to take my jar here. I'm going to ask Math Dad to shake it for me one time. And then we're going to have to let it sit for about a half hour. And when we do that, something really cool is going to happen. And we'll come back to that in just a minute and I'll show you. But I am seeing, Math Dad, a whole bunch of requests for you to sing a song called Row, Row, Row Your Boat.
Okay. Here goes. I'm singing a song, I don't know the words. I don't know the words to this song. I'm singing it loud and I'm singing it long, but I don't know the words to this song. No, I don't know the words to this song.
That is not Row, Row, Row Your Boat.
Are you sure?
Yes, and now it's going to be stuck in my head all day. All right. I saw a real good question in the chat. Someone asked, what is water's element? And that ties in perfectly to what we're going to talk about next while we're waiting for our rubbing alcohol and salt shaking experiment to sort of settle out. So what is rubbing alcohol? What is water? And I'm going to have ask Math Dad to do one more of these. So we're going to do one of them that had a lot of salt and one of them that has not quite as much salt. So if you will pour rubbing alcohol into that and shake it while I bring this around to the whiteboard, and we're going to answer that question. What element is water? So here we go. So elements. An element is just one type of atom. So if you look at something like gold, element. Gold is a single type of atom, and when you have pure gold, you just have lots of that single type of atom together. Another element is called oxygen, is actually a compound. So here is oxygen. Oxygen has a bond that keeps those two molecules together. And a gas that is similar to oxygen, nitrogen, that we all breathe, is also what we call diatomic. That means two atoms, di for two and atomic for two atoms, and they're bonded together with a triple bond. And I'm actually going to erase my oxygen here and show you that the oxygen has a double bond. But when we talk about oxygen gas, it's a pure element because the only atoms that we have here are oxygen. Same thing when we talk about nitrogen gas. It's a pure element because the only atoms we have here are nitrogen. And then, of course, if we had gold, we would have gold atoms. And if we have something like helium gas, we'll have just a single helium atom because it is very happy to just be by itself.
But what about hydrogen?
Hydrogen forms two, just like a little bond there. So there's hydrogen. Just like oxygen and nitrogen are diatomic, so is hydrogen, because a hydrogen atom all by itself is not a happy camper, but hydrogen is still super reactive, even if you have H2. And now that I'm saying that, I'm like, oh man, I want someone to fact check that because it's been a little while since I have looked up that. Now let's go and talk about a compound next, because a compound is different than an element, and this is what water is. So if you have an element and you were only going to have pure elements, you would run out of new things after about 118, although I'd say you can't even quite go up to 100 because a lot of the bigger elements are not stable. You would never see large quantities of those anywhere naturally. So if you're talking about just pure elements, we run out of things pretty quickly. There are only going to be, a few dozen stable things that you could see and have to put together and build your universe from. But fortunately for us, we have so many different types of compounds or larger molecules that are made of more than one element. And water is one of these, one of my favorites. So water is H2O. We have the oxygen here. That's the O part of our H2O. And then the H2 means hydrogen. We have two hydrogens here. That is water. And now, just for fun, let's do a little, let's do a fun little prompt, and I'll try and have Math Dad fact check me on this. So you guys in the chat, give me a compound, and I'll see if I know what it is. So give me a compound. Sodium chloride is the first one I saw. Sodium chloride is a compound, and it is NaCl. So we have one sodium, and then we have chloride, and that is also table salt. That's what plain salt is, sodium chloride.
So the answer is in the name.
The answer is in the name. So whoops.
Chloride.
And you're right, salt is sodium chloride. So give me a different compound, a compound where there is not the name in the answer in the name. So I'm seeing uranium, that's an element. Give me a compound.
So I know one, like ammonia, like the cleaning substance.
Ooh, that's a good one, ammonia. So Math Dad knows ammonia, the cleaning substance, and he's like, well, what's that made of? Is that an element? No, it's not an element, it's a compound. And now we're gonna find out if I remember off the top of my head what ammonia is. We did not plan this in advance, and I'm pretty sure that ammonia is no, it's nitrogen based. So I was thinking of methane, CH4. I think ammonia is NH3. So we would have one nitrogen, and then we would have 3 hydrogens. That's what I think ammonia is. Fact check me, am I right?
You are correct, NH3.
Yes, Science Mom for the win. Any other, we'll do one more. So give me a bleach. Bleach is a good one. All right, what is bleach? I believe that most bleaches contain chlorine, like Clorox. I'm guessing Clorox is called Clorox because it has chlorine in it. This one I'm actually not sure, so I could give a wild guess. But I'm asking Math Dad if he'll look it up real quick.
Okay.
Bleach.
NaClO for sodium hypochlorite.
Sodium hypochlorite. So the sodium, the chlorine, and then the oxygen. And then I'm guessing that when you put this in water, you are going to get a lot of what we call hydroxide ions. So if you have an oxygen and a hydrogen together, then they have a negative charge, and they will, if you have a lot of them together, that creates a pretty hostile environment. That's something that for you or me, if we put our hand in it, that is going to be bad for our cells. And we're going to talk a little bit more about these guys when we do acid and base chemistry on Thursday. But thanks for interacting with me in that quick little, like, can Science Mom draw the compound? One of the things I love about chemistry is that if you know, there's certain names that if you know, you can actually guess what things are. Have you ever looked at the back of a shampoo bottle and been like, what in the world are all those long words? Well, if you know chemistry, you can actually kind of piece together what the molecules are, because those names will tell you what the molecule is made of, which is pretty cool. And that's another thing that we'll be talking more about next time. I want to give a quick shout out to Science Mom Liza and Krista and Emily, and tell you guys something kind of funny. So Science Mom Krista and I and Emily and Liza, each day after we do QuaranTIME, we have a little chat about, like, you know, how did it go and what were the comments like in the chat. And Science Mom Liza told me that yesterday there was this kind of like conversation back and forth with the people on YouTube trying to get the video up to 100 likes, where they're like, come on, we just need a few more. Who's going to give it a like? And I thought that was really great. You guys have our back. Thank you for looking out for our channel metrics. And now it's time.
So I have a question.
Yeah.
So with water, it was H2O, whereas with ammonia, you wrote it NH3.
Mm-hmm.
How do you determine what order to put those in? Why wasn't it H3N?
And why isn't it OH2 for water?
Yeah. What? Any idea why?
I used to know that, but I don't remember.
So there's actually a reason, and it's not just because they had to do something? Or?
Yeah.
Okay. No, I was just curious.
Yeah, I think there is a bit of a reason, and generally, I mean, H2O is a little bit of an exception, because usually if you have a subscript, it's going to be later in the molecule name. But I don't know.
Yeah,
I'll have to look that up.
I've seen as well. Are you going to talk about the charges and why some of those bonds are going? Is that another day? Or?
Yes. Yeah.
Okay.
We'll get into that a little bit later. But I wanted to check out our layers here and see if they've worked. And one of them has. So here is this jar where we had the salt and our here, I want you to hold this. I gotta find out.
The rubbing alcohol?
Coloring. The rubbing alcohol, yes.
Okay.
And where did the food coloring go? Do you see it? Oh, there it is. Okay. Now, just in case this is difficult to see online, although I think you guys can see pretty well that there's like a white cloudy layer there, and then we've got a clear layer. Here's what happened, and this is so cool. we had those salt ions start mixing with the water, and they like the water better than the rubbing alcohol likes the water. Rubbing alcohol will mix with water, but not super, super well. And if you add salt.
So just like the water, so we had 50% rubbing alcohol. So does that mean that the other 50% is water? Is that what you're saying?
It was rubbing, yes.
50% was rubbing alcohol.
50% was water.
And 50% was alcohol.
Yeah. And then we added salt, and the salt really likes the water and binds with it. And so then it settles to the bottom and the rubbing alcohol floats on top. And just in case this isn't super visible, I'm going to drop a drop of food coloring in there. Oh, we need like a white background. Here. Did you guys see that? Isn't that cool? So this is a really simple experiment that you can do at home if you have salt and rubbing alcohol. That's all you need. And if, like I said at the beginning, if you happen to have 50% rubbing alcohol, but you need a more concentrated form of rubbing alcohol, you can actually just pour off this top layer, and there's your now more concentrated rubbing alcohol. It gets it much more concentrated than 50% because we took all this water out here that we can just leave in the bottom. You can pour off that top layer. Isn't that awesome?
That's pretty cool. I'm impressed.
Yeah, so cool. Now, we started talking about it just a little bit as I was having Math Dad hold this. You could just set that right there. But I want to show you guys a video that I took yesterday, because yesterday I introduced a bit of a mystery, and we will talk about this science mystery, and then we'll get on to the next part of our show, which is the fact or fiction. So let me share my screen with you again. Share screen. And then we get that kind of crazy, like infinity going on forever with my board. And now we're going to come down and play a short video. So here we have a plate of water. If I drop in just a little bit of rubbing alcohol, you can see that you get this circle in the middle where there's no water anymore, and it looks kind of flat. And then if I add a little bit more rubbing alcohol, there we go. There's that crazy pattern I was talking about. Isn't that sort of mind-blowing? So all around that edge, you get this crazy motion back and forth where the water and the rubbing alcohol are starting to mix together, and then it will sort of calm down a little bit. And if you want to, if you wait long enough, it will actually mix all the way together. But I got a little impatient, and I was like, oh, I'm just going to make it mix on my own. And if you stir it together, rubbing alcohol will mix with water. But if it takes a little bit of help, isn't that awesome? Now let's talk about why that works, because I showed it to you guys yesterday, but when I was trying to show it to you yesterday, we were using this web camera and I was trying to hold a plate, and I didn't know if you got a very good view. So I wanted to show it to you again. And I'm curious, did anybody have time to do some research on why this happens? Because this is a really cool effect. Oh, and I see someone saying, if everyone likes it, we can hit 1,000 likes. Amazing. Anybody? Does anybody know why that happens? I'm going to ask Math Dad to see if he has a guess, and then we'll explain it. So Math Dad, what's your best guess?
Okay, my theory here is that maybe some gas is being built, like on the baking soda thing, only just no bubbles, and so it's like there's some chemical reaction going on, and it's making a gas.
Chemical reaction going on and making a gas. Wrong. That's not happening. Do you have another guess?
Oh, I meant it's making another liquid, because that's what's happening.
That's true. We did not see any bubbles, so gas went. Nope, no new liquid being formed.
Okay. There are tiny little gremlins floating in there, and they're kicking really because they're trying to get away from that yucky
rubbing alcohol.
Yeah.
That's really creative and fun. There are no gremlins in the water kicking to get away from the rubbing alcohol. We're gonna come over to the whiteboard and
all right,
we will
chat, help me out,
explain it.
I give up.
All right. So baking soda plus vinegar that we did, where you saw all the bubbles, that was an example of a chemical reaction. But salting out, taking 50% rubbing alcohol and concentrating it more, where we saw that cool layer of, the rubbing alcohol up here and then our salty water down here, that's actually not a chemical reaction. And to understand why that works and why you see that really cool effect when you drop rubbing alcohol onto a plate of water where the water is nice and thin, we need to know a little bit more about the chemistry of both of those molecules. And this is why I love chemistry, because if you understand chemistry well enough, then you can totally figure out why these things are happening. So just like we did yesterday, I'm going to draw up the chemical formula for water. Water is H2O, and I'll use different colors, so hopefully it's a little bit easier to see. So there is our oxygen, represented by a black circle this time, our hydrogen, represented by these red circles, which hopefully are visible enough. There's our water molecule. Now, the thing about water and the thing about oxygen that you need to know is that oxygen is kind of greedy. So oxygen, when it is all by itself, it's like, I want the electrons. The electrons are all mine. And we call that electronegative. Hydrogen, on the other hand, not so electronegative. And so when you have your oxygen molecule, or your water molecule, excuse me, you end up with all the negative charge being up in this area. This part is negative, and because all of the electrons are spending all their time around this oxygen molecule, this part down here ends up being kind of positive. And this has a huge impact in how water behaves, because each water molecule, since it has this negative and positive, when it finds another water molecule, it's like, oh, best buddy, we can put the negative and positive together, and just like magnets, we can stick. And then if we look at rubbing alcohol, on the other hand, rubbing alcohol has an oxygen. It also has a little hydrogen attached to that oxygen. But then instead of having another hydrogen, rubbing alcohol has 3 carbons attached to it. And these 3 carbons are not positive, not negative, they are neutral. And so when you have these neutral things here that interact with water that has positive and negative, they don't really like each other. And if rubbing alcohol did not have this part here that does have a little bit of a negative charge, then rubbing alcohol would not mix with water. It would just be like when you pour oil on water and the oil doesn't mix at all. Oil is just carbons and hydrogens, does not mix with water. Rubbing alcohol does, because it has this little bit of negative here. And now,
so wait, let's clarify. So you're saying that this is not a chemical reaction because the water molecules stayed water?
The water molecules stayed water. Rubbing alcohol molecules stayed rubbing alcohol. We did not get a new thing formed. We didn't form a new product in here, and we did not form a new product when we put the rubbing alcohol on the plate.
So if it's not a chemical reaction, what type of reaction is it? Or is there a name for that?
A physical reaction.
Okay.
So we had a physical reaction. And now let's take a look at our plate, and we'll explain how the plate works. If you want to go into more detail on how rubbing alcohol forms that little empty space in the middle of the plate and why you get that crazy reaction, look up the Mangoni effect. Mangoni.
Would you call me?
Effect. It's named after an Italian scientist. And will you check the spelling on that for me real quick, Math Dad? Mangoni effect. It might be Mangaroni effect, but I'm pretty sure it's Mangoni effect. So here's how it works. When you are looking at water molecules, and I'll just draw little blue dots for the water molecules, water has incredible surface tension, and you can kind of think of it as like you've got 20 people in line, and they're each doing a tug of war with the other person.
Marangoni.
Oh, man, I did spell it wrong. Marangoni, not Mangoni. There we go. M-A-R-A-N. Marangoni. There we go.
That's right.
Marangoni effect. Thank you, Math Dad.
Whoa.
Okay, so water is like having a whole bunch of people in line and having an intense tug of war where each person is pulling a rope between them and the other person and the person behind them. This would be a seriously challenging tug of war because you'd have to be going like on both sides and everybody's doing that. That's what gives water its strong surface tension. So imagine you've got these water molecules here that are all pulling, and then in the middle, you're going to drop some rubbing alcohol. And the rubbing alcohol does not have strong surface tension. So here's our rubbing alcohol. And it's like, I'm not going to pull onto those ropes at all. What's going to happen? It's going to pull, the water is going to pull to the sides. So you have the water pull this way and pull this way because it has strong surface tension. And then you end up with this low spot in the middle because the rubbing alcohol does not have strong surface tension. And again, the reason why, it all has to do with those molecules and how they behave. It's really cool.
Okay, so the water is pushing away from the rubbing alcohol, but that just moves things again, and then it just happening over and over again, and that's why it continues?
and the reason that you see that crazy swirling if you put enough rubbing alcohol there is because rubbing alcohol will mix with water, but the way that it happens causes some chaotic patterns, and so that's why you get that swirling right there. And then if you shake it all around, you can get the rubbing alcohol to go all the way into solution where it's completely mixed in, but it's mixed in because we have, here's our rubbing alcohol. And we'll do the water up here, and here's a water molecule. So these parts of the rubbing alcohol right here, they like the water, but the water is not a fan. So like angry eyebrows here on the water, it is not a fan of this section. And so if you add salt into water, which water loves even more than rubbing alcohol, it will be like, you know what? It's been nice hanging out with you, but I'm going to go hang out with salt instead because I like salt better than I like you. And that's why you can salt out rubbing alcohol and get that layer. Now, I have gone a little longer than I usually do with my science lesson because I was just so excited to tell you about all that chemistry. So we're going to wrap it up there with one homework assignment for science that you can do, and that is to put an egg into vinegar. If you take an egg and just put it in a jar of vinegar, you will find out that you get small little bubbles. And those bubbles are a clue that we have a chemical reaction happening. So if you'll just plunk that egg right in there. Oh, carefully.
You said plunk. Plunk doesn't mean careful.
That's true. Plunk does not denote the word careful, but look at all that. Can you see those bubbles? So we've got bubbles forming around the egg, and tomorrow we will find out why and what's happening. So that is your take-home kind of assignment for the chemistry.
Should it be a raw egg or a hard-boiled egg?
It can be raw or hard-boiled, but I recommend raw. And if you would like to, you can actually eat this egg after we do our experiment with it. But if you want to eat it, make sure you put it in your fridge. If you're not going to eat it, it can be out on the counter, and what's happening will happen a little faster. But if you want to try eating it when you're done, make sure keep it in your fridge.
Will it taste like vinegar?
It is going to taste like vinegar if you decide to eat it.
Okay.
You've tried it before, remember?
No.
I
must have blocked out the painful memory.
We blocked it out. All right. Who is ready for fact or fiction? Are you ready for fact or fiction, Math Dad?
I am. So there have been several questions that came in. Should we save those?
Yes, we'll do fact or fiction, and then we will answer questions. All right. So I had a chance to research these, and if you pulled up our handout, which I will ask Science Mom, Krista, Liza, and Emily to drop in the chat on Facebook and in the chat on YouTube, there is a link to this little handout that you can print. And yesterday, I also made a little answer sheet that has more information on the fact or fiction. So hopefully you didn't read those yet, because then you're in the same place as Math Dad and you get to give us your best reasoning and guesses for each of these. So fact number 1, is this true or false? The Earth is a giant magnet.
The Earth is a giant magnet. Okay, so I know that there got the North Pole, South Pole. You got a lot of things going on. I don't know the technical definition of a magnet, but there's literally a magnetic field. Yes, it's got to be true.
It is true. It is true. The Earth really is a giant magnet. And like you mentioned, North Pole, South Pole, and magnetic field that goes around and protects our atmosphere. Absolutely, Earth is a giant magnet, all thanks to the fact that we have a nickel iron core that is rotating.
So that doesn't have any, we're pulled toward the Earth from gravity, and that's independent. That's a different idea than magnetism, right?
Yes, okay. Exactly. So the magnetic pole of the Earth, or the magnetic field of the Earth is not responsible for gravity, but it does give us North Pole, South Pole. And if you want to look up something really cool, look up pole reversal, because the North Pole and the South Pole actually switch places every few millennia or so, and we don't know why. Isn't that crazy?
That's kind of weird. Like, does that mess with electronics?
We don't know.
Whoa.
We don't know. But our North Pole and South Pole do kind of wobble. They don't stay in the same place. And if we look back, like in geological records, because iron, when you have lava pour out, the little iron particles will line up facing north and south. And every so often you'll see like lava flows where they're all lined up this way, lined up this way, lined up this way, and then all of a sudden lined up the opposite way because the pole switched places. And we can find, like in the rocks, we can see this record that this has happened a lot of times, but nobody knows why. Last I checked, nobody knew why. Maybe we're finding out. And if you are a scientist, like grow up to be a scientist, maybe you'll be the first person to discover this is a really cool thing.
Somebody put a big comment here. I wanted to read this. I'm scrolling too fast. The crust of the Earth has some permanent magnetization.
And Earth's core generates its own magnetic field, sustaining the main part of the field we measure at the surface. So we could say the Earth is therefore a magnet, but permanent magnetization cannot occur at temperatures above 650 degrees Celsius. Thank you, Katie. I love that clarification. Awesome.
Yeah.
Are you ready for fact number 2?
I'm ready.
A cloud can weigh more than 1 million pounds.
Okay. A cloud can weigh more than 1 million pounds. Well, I mean, of course, that sounds crazy because you think of clouds as light and fluffy, but if you've got this huge thunderstorm, but the water's literally up there in the cloud, and they can dump crazy amounts of water, so true.
Very well reasoned, Math Dad, and that's exactly right. If you think about the amount of water that comes from a big thunderstorm, I mean, if you have a rainstorm that rains 10 inches, I actually mathed this out yesterday, 10 inches of rain over 10 square miles ends up being more than 1 million gallons of water, and that's going to weigh more than 8 million pounds. So yes, clouds and all that water came from a cloud. So clouds can definitely weigh 1 million pounds or more. But the reason why we don't think of them as like, well, why don't they fall from the sky? And it's because they're not all connected together. It's tiny little droplets, like all in a big bubble.
You also just said 10 inches of rain. So that's like record breaking. Like most places on Earth would never have seen that much.
Yeah, 10 inches of rain is like hurricane monsoon level rain. That's true. Most clouds are not quite that big, but clouds definitely can be that heavy. All right. Quick shout out to everybody who got that in the comments because I saw a lot of correct answers there. Third one, rats laugh when being tickled. True or false? Rats laugh when being tickled.
I don't know. My kids used to laugh when I tickled them, and now they're like, Dad!
Math Dad hates being tickled.
That's true.
True fact. Like, yeah, when we first started dating, I was like, oh, like it would be all fun if I like tried to tickle him. And I got pinned with my arms behind my back so fast at the look on his face, he was like, don't ever tickle me. He gets really grumpy if you try to tickle him. But rats are not grumpy like Math Dad about being tickled. They actually seem to like it. And this is true. Rats appear to laugh when being tickled. And there's a great video that I linked to in the little answer key that you can find on Patreon, a National Geographic documentary where they show a lab, a person kind of rubbing the back of a rat, and you can hear the sound of it laughing. And then the rat, when the hand leaves, the rat's looking up like, where'd you go, friend? Come back. And as soon as the hand comes back, the rat runs back over to get tickled again. Really kind of cute. So we think, I mean, we can't like ask the rat and have the rat tell us that that's laughter, but it really sounds and looks like laughter.
Well, my guess is then that most animals probably like tickling. I don't know.
I think a lot of animals can laugh. I think quite a few. Maybe I should qualify that. Quite a few mammals, and I don't think reptiles are going to laugh, but I think a lot of mammals can. All right, last one. Eating a lemon daily prevents you from being sick. If you eat a lemon daily, that prevents you from getting sick.
Okay, boy. I mean, fruit is good for you, right? And I know about scurvy. So if you're on a ship and you don't get any vitamin C, you come down with scurvy.
True.
Or, you don't have to be on the ship. You need vitamin C.
Yep, you need vitamin C. That's why it's a vitamin.
Okay, sure. I mean, it's not bad for you. A little lemon. I mean, it might give you a sour face, but true.
False.
What?
Yes. So I see this one. I see this one pop up on my Facebook feed seems like every 3 months. Someone will be like, oh, I just discovered that if you take a lemon and eat it raw, boil it in water, like whatever, there's always some sort of way to prepare the lemon, and eat one every single day, you won't get sick. And I secretly wonder if there is some lemon farmer somewhere who's like, aha, this is going to be the secret to my success, and is just trying to push this out. I don't know. But no, it's not true. There is no such thing as a food that you will eat every day that will prevent you from ever getting sick, because getting sick has to do with viruses and bacteria that you're exposed to. And if you get exposed to a virus or a bacteria that your immune system doesn't recognize, then it will start to multiply and divide and get bigger. And it's up to your immune system to fight it. Does eating healthy food and getting enough sleep help your immune system? Sure. But is a lemon a miracle cure? No.
Wait a minute. So what was the actual question?
The actual statement was, eating a lemon every day prevents you from getting sick. That is
Oh,
false.
it doesn't. Okay, it can't actually prevent the sickness.
No.
It could stop scurvy though.
Yes. So
Okay.
if you were having scurvy, a lemon would help a lot. But in the absence of vitamin deficiency, false.
So they're good for you, but yeah, they're not going to.
They're not a miracle.
To fight off the germs.
No.
Okay. No. Fair enough.
All right. Let's take a couple questions. You said that we had some questions coming in from our.
Yeah, they've been saved up in the chat here.
All right. We'll answer a few questions and then we'll get to our engineering challenge and the drawing prompt for tomorrow.
All right. What's your favorite element?
Oh my goodness. That's such a hard question. What is my favorite element? I'm going to say carbon, because carbon is the building block of life and you can make so many different things with carbon. So that's right here, 6 protons, and you can have, carbon's just really cool. So carbon-12 is like the common form of carbon that we use most often, but carbon-14 is used with like radiometric dating, like trying to figure out how old things are. That's one cool fact about carbon. Did you know that diamonds and pencil lead are like pretty much the same element, just arranged differently? So when you write with a pencil, you're using graphite, and that's pretty much pure carbon. But the atoms are all like disorganized. They're not together in a nice pattern. But a diamond is pure carbon with them arranged in a really nice crystal structure because of the high pressure that you get underneath. And so that's kind of cool. I don't know of any other element where you have essentially the same chemical formula, but 2 such different results just depending on how the atoms are arranged.
All right, carbon it is.
That's my first answer. I could probably come up with several more.
Why can't you breathe underwater? It has oxygen in it.
That is a great question. And why can't you breathe underwater? It has oxygen in it. It's because we do not have gills. The gills that a fish has works very differently than the way that our lungs do. And because it allows water to just sort of pass through these membranes, and then those membranes kind of pull out the oxygen from the water. And with the way that our lungs work, they're designed for air. They're designed to bring air in and push air back out, and the water's just too heavy. So we can't breathe underwater because our lungs are designed for air. That's the best answer.
Even liquid oxygen?
Liquid oxygen is so cold.
It's cold? Oh.
Yeah, like that would be terrible. That would be terrible.
I think I saw it in a movie once.
We can't breathe liquid oxygen. No.
How are atoms made?
How are atoms made? In stars. This is one of my favorite like cool blow your mind facts. So stars are mostly helium and hydrogen, but when a star goes supernova, it collapses down and you get this reaction that just explodes the star, but it also makes heavier elements. Everything heavier than iron, I'd have to fact check really quick to remember what it was, but everything beyond a certain element, and I want to say iron, but it might be even earlier than that, was made in a star. So a lot of the atoms that are inside you are the result of supernovas that happened probably millions of years ago. So that's the main way that we get different atoms in the universe, is through supernovas. Kind of cool, right?
I did not know that.
Learn something new every day.
That's right. How are black holes made?
Very, very heavy stuff going smush. That's my scientific answer.
Yeah,
no, they're like a gravity trap. So if you get something big enough, a black hole will form just because it got so big and so heavy
that it collapses.
Collapses on itself. Yeah, black holes are crazy. We'll talk more about that when we get to astronomy.
Does the egg jar need a lid, by the way?
Oh, good question. Does the egg jar need a lid? No. The only reason to put a lid on this is if you want to avoid like a little fruit fly or something accidentally landing in there. It does not need a lid. If you do put a lid on it, I would say just set something on like this, but don't screw it down because you are forming a little bit of gas. It's not going to be enough to break the jar, I'm pretty sure, but you want to make sure that that gas can escape if it needs to. So just set a lid on top. Don't screw a lid on.
Good clarification.
All right, you guys ready for the engineering challenge? Yes, yes, yes. I'm seeing people say yes.
Whether or not you are, it's coming.
It is coming.
So I do that all the time with my students. Are you guys ready for this? It doesn't matter what they answer. I'm just going to give them the problem anyway. So it's like the illusion of control, but you don't have any control.
It's courteous to ask. We are going to do the engineering challenge anyway. But yes, I hope you're ready and I hope you're looking forward to it because we have a fun engineering challenge today. Get our computer set up down here and turn it to face our table. so that you can see us, and then we'll move these jars. And I wanted to say, so yesterday during our engineering challenge, we told stories about the first jobs that we ever had. And I was like, man, we should make a little clarifying point so it doesn't sound like Math Dad's parents violated child labor laws.
There are no child labor laws on farms.
So in case you're watching and you have never been to like a small family farm, I'll just say that family farms, like, it's tough. It's really tough to make a living as a farmer. And if you grow up on a farm, you're going to be working on that farm. And Serge is really appreciative of the fact that he worked the first $2,000 he earned. He worked 2,000 hours to earn that because it really taught you a lot, right? Good work ethic.
You know, I know how to work hard now.
Yeah.
Yeah. On a farm, you work until the work's done. So you might as well work hard so you've got some time to do something else.
Yep.
And
so it was a good experience.
It's a lesson I'd like my kids to learn maybe a little bit better. Just you work hard and then you play hard.
We should throw up I'm going to pull up our engineering challenge so you can see what it is. Today, we are going to make a Da Vinci bridge out of pencils, or you can use popsicle sticks or anything else that is long and sturdy. And the rubber bands are used just to help the sticks not to slip. And if you do this engineering challenge, see how much weight it can hold, and then you can take a picture and post it online, where I bet that you guys will make better engineering Da Vinci bridges than we do because we're kind of under a time crunch. No. Do you know why this is called a Da Vinci bridge?
My guess is that Leonardo da Vinci came up with this design.
He did, and the story behind it is actually pretty cool. So Leonardo da Vinci was an artist and a scientist, and back then, you didn't get to be a scientist by writing grants and getting funding or working at a university. You got to be a scientist by having patrons, wealthy people who would be like, your ideas are cool, I will give money to you. And so Leonardo da Vinci would occasionally, people would commission him. They would say, will you do this project? And he would send them something, and then he would get paid for it. And the emperor is probably not the right word, the leader of Turkey at the time, which was not called Turkey back then, asked him to build a bridge near Istanbul. And the bridge was going to be huge and span this big thing. And Leonardo da Vinci submitted a plan, and they looked at his plan and said, that's crazy, it would never work. And they didn't use it. But if they had, it would have worked, and it would have been the tallest, longest freestanding bridge in the world. So here is the Da Vinci Bridge.
So I've got a bunch of pencils, and I have a rubber band in 3 locations. I may not need all 3 locations, but it's just to keep the pencils from sliding across each other.
Yep. And I'm going to be using popsicle sticks. Wish me luck.
Okay.
So you start out by making like a little box, and you're going to do a lot of like over-under things. So I put 2 lines this way, and then I put 2 lines this way, and put other popsicle stick underneath. And we did link 2 videos in the notes. So if you get the notes that we posted on Patreon, you'll have much easier to follow instructions in those notes. And then once you get your little grid, you're going to lift up the bottom one and stick your other popsicle sticks in and just weave them underneath. I will say this is a little tricky to do just with 2 hands.
We might need to join forces.
This might need to be a collaborative effort. We'll find out. We'll see how we do. I got it.
Yeah, I'm doing just fine too.
I got my first little set here. Now
this would have been easier if pencils weren't sharpened.
Yeah, so if you happen to have a pack of unopened pencils, those are a lot easier to do with. It almost seems like a little bit of a safety hazard to be doing it with sharpened pencils, but that's all we had. And that's like the motto of the month. You do what you can with what you have, right?
That's right.
You will adapt.
I will survive.
Okay.
That reminds me of another song. I'm singing a song, I don't know the words. I don't know the words to this song. I'm singing it loud and I'm singing it long, but I don't know the words to this song. No, I don't know the words to this song. Boom.
I know the words to a song that you should sing. Baby Shark. I'm seeing so many requests in the chat for Baby Shark. I'm not looking at the chat right now, but last I looked, there were at least 2 of them.
Baby Shark, is that the one that goes, I'm singing a song, I don't know the words. I don't know the words to this song. I'm singing it loud and I'm singing it long, but I don't know the words to this song. No, I don't know the words to this song. That was it, right?
That was not it. Hey, look, I've got my bridge. Turn it sideways so you can see. And look, it's off the ground and ta-da-da-da-da-da, it will hold weight. I'm gonna try and see if I can build one more level into it. So when you put your new level on, it helps to like lift up, and then you're just weaving in the other popsicle sticks. So you have like one over and one under. It is a little tricky, but it's also quite a fun challenge. I'm enjoying this one. Okay. My bridge is taller now. I did another level. And oh man. And then I had a popsicle stick slide and the whole thing collapsed.
Yeah, mine was doing all right. And now I've lost structural integrity.
All right, so I think we should see if Science Mom's bridge will hold duct tape and the phone, because that's fairly heavy. Hand me my phone.
All right.
So duct tape, my phone. Oh, did you do that on purpose?
No, it was weighted poorly. But
okay, like I said, I bet you will be able to make much better Da Vinci bridges because you won't have saboteurs stacking weight on them unevenly, and you'll have more time. Now,
I just did what you told me.
Should we work together?
Yeah, let's work together.
All right.
See what we can do here.
Collaboration for the win.
Okay, so I'm just going to keep weight on it, and I'll let you do the sliding.
Okay. There we go. So we're weaving in our next set. We have the first little arch, and it's stable. Now we're going to try another one. So we slide our pencil underneath, and now we're going to lift up that underneath pencil, and I take my two next pencils, and I just weave them like under, over, under, over. Uh-oh, but our rubber band is not low enough on this one to like catch. Hold on, let me scoot the rubber band down just a little bit. And the purpose of the rubber bands is just to help the pencils not slide. Okay, 3 more. We're gonna do another one.
All right.
So here we go. We put this one underneath.
Okay, then I can use it to
lift up
while keeping pressure so things don't fall apart.
And then we go under and over, under and over, and there we go. Put it down. Okay.
Oh no, one of them went sideways.
Yeah. Went sideways. So
the sharpened tip did this in.
Did we have the sharpened tip down on the bottom? Oh, so if you have sharpened pencils, sharpened tip on the bottom.
Bad idea.
Yes, yes.
That makes sense.
That's kind of tough.
All right. So, well, I'm curious if you guys can do any better than that.
I'm sure they can do way better than that. Do you know that yesterday we had several people send us videos of these infinity cubes? And they were amazing. So the infinity cube that we made yesterday, we sort of went through pretty quick. But several people yesterday, they had pictures. A few people made them out of dice, but there were some made out of paper that just looked amazing. And then in the videos, they were just going like super fast.
Nice.
Now our drawing prompt for tomorrow is...
It's a good idea to share that because we forgot last time.
Yes. So we're going to share it, and Math Dad and I are going to do it real fast because Math Dad needs more practice drawing. So it's to make a rainy day card. So you accordion one piece of paper, put it in the fold of the card, and that's your umbrella. And then draw who's holding the umbrella and why. And if you want to, you can totally go like cloudy with a chance of meatballs direction and have really crazy weather. You ready for this, Math Dad?
Yeah, of course I know what I'm doing. What are we doing?
Drawing. Because yesterday when you were drawing your immortal hippo, you were saying that you would love to be better at drawing and you need more practice. So this is practice.
Yeah, okay, practice is good. Practice is good.
Practice is excellent. And I recommend making your accordion first and then draw your picture. And after you draw your picture, then glue it in. Because if you put your accordion in and glue it, and then you're trying to draw and the card is folded, then it's quite a bit trickier to do. So that's what I would recommend.
That sounds like good advice.
And then I'll pull up the chat again real fast.
My sister just got back to the U.S. She'd been off in, where was she?
Thailand. She was in Thailand. Just got back.
Yeah.
Baby shark do 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 do.
Baby shark do 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 do. Baby shark do 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 do.
Baby shark. Daddy shark do 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 do. Baby shark do 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 do. Baby shark do 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 do. Baby shark. Now you're supposed to do it like a baby and then like brother, sister, mommy, daddy. Yeah.
Grandpa shark do 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 do. Grandpa shark do 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 do. Grandpa shark do 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 do.
Grandpa shark.
Yep.
That's the way the song goes.
All right. I probably needed more folds so it could open further.
Which way did you fold it? The long way?
Yeah, I did this.
That way?
Yeah, I think I just made them too big.
Too wide? It should still work.
All right.
It should still work. No worries.
All right.
I've seen several questions in the chat asking about our kids. We have 3 kids, but we don't plan to have them on the show. On the show it'll be just us, but maybe on Friday I'll load some pictures and we'll tell you a little bit more about our family.
Yeah, I mean, eventually they might be on, but yeah, they've been pretty good to stay quiet and to stay off the internet so they don't eat up our bandwidth. Yeah.
Oh, I drew my person a little funny, but that's all right. We'll just go with what we got. So I have to tell you, I use an umbrella way more now living in Nevada than I ever did anywhere else, because in Nevada in the summertime, it is really, really hot. I'm talking, we get up to like 115 degrees. It's Fahrenheit. And so in the summertime, when I'm walking, or even in like spring, when I'm walking the kids to school and back, if I have an umbrella and I have shade, that feels so much better when you're walking in 110 degrees weather than if you have, than if you don't have shade.
So you use it as a parasol.
I do. And actually the very first umbrellas, I think were made in Asia, and they were used for shade from sun. I'm pretty sure about that. Haven't fact checked it recently, but ooh, Matt's dad's got some cool stuff going on over here.
Can't draw and talk. Pressure's on.
So I drew my person, and I drew a little umbrella stick that they're holding, and a sun, because they're going to be using their umbrella for shade. And now we're going to stick the umbrella on.
And I'm trying to draw a leprechaun trap. So I've got this big thing of gold, the cage that's ready to fall on it.
Nice.
And the leprechaun will try to take shelter underneath
the umbrella.
Silly leprechauns.
Oh, I like it. And I'm gonna make my umbrella just a little bit smaller. So I'm gonna cut off part of my accordion and put my tape on. Nice double-sided sticky tape. There we go. Oh, right. Where did it go?
Right next to me.
Yep.
The last place I would look. Oops.
And
I see why you cut it shorter. Yeah.
Yeah, there you go. You can cut yours shorter too.
All right.
We've already seen a couple fantastic submissions for the rainy day card, and I'm really excited to see more come in.
Wait, already?
Come in soon. Yes.
How did they know?
I posted it on Facebook. Math Dad is not on Facebook.
No.
Nope.
No
So,
Facebook for me.
Here's my card. So we've got a little person, and they've got crazy hair because I accidentally drew the arm like way too high, and I had to move their head down. But crazy hair person holding a little umbrella and sunshine.
Here's mine that can't open very far because I didn't make enough folds in it, but it's covering the pot of gold, so the leprechaun will come up and get captured.
Nice job, Math Dad. See, you do have drawing skills.
That's right.
But not as amazing as the people who are watching our show. Their drawing skills are incredible. You ready to see some more line art?
Yeah.
All right.
Let's see what they've got.
Come on over here, and I'm gonna share my screen with you, and then we will pull up more line art because these line art drawings were amazing. So here we are. We'll play again. So we have a Go Science line art drawing where they totally kept it connected the whole entire time and managed to write words as well as draw. Writing words and keeping your pen connected the whole time is pretty challenging.
Yeah. From lowercase to uppercase.
Yeah. A nice swirl here that they colored. Excellent job, Lily. And then I love this one. We've got a person with like kind of an arbor over them and a horse. A beautiful landscape. And a cat. Well done, you guys. Yay, basketball. And I love how they even did the scoreboard there too. This one was a fun set. 2 flasks. Nicely done, Ethan. And I love the way that they're colored. Chase the Wolf, inspired by her dog. Beautiful, Carissa. I love this one.
Wolf name, right?
Yeah. Isn't that great? And then a more abstract piece here that I think is colored really beautifully. Like, seriously, I'd put that on my wall.
Yeah.
This single line drawing from...
Like a map of the U.S.
Yes, it totally does look like a map of the U.S. Great job. And then this guitar, amazing. Isn't that great?
That's one line.
And I love that the music notes are incorporated into the guitar. That's beautiful.
Yeah.
Yummy bowl of noodles. I love it. And then a flower. And it is tricky. It's definitely tricky to draw without lifting it. But Kinley, I love these balloons all connected in the middle. I thought that was great. We've got a Minecraft-style dinosaur. Very nice. And look at that.
Yeah, Matt Dad.
Matt Dad singing a song and I don't know the words.
All connected. Nice.
I wish you guys could see Matt Dad's smile. He really liked that one. We've got a blimp. Very nicely done. A beautiful dragon. The ice cream. Isn't that incredible?
Whoa.
Drippy ice cream. I love that one.
So consistent.
Yeah. And then we've got a great collection here of some, it looks to me like...
video game characters.
Yeah. Is that Sonic the Hedgehog? That's what it looks like to me.
I think you're right.
Yeah.
I see Kirby there.
Nicely done. And then they trace their hand, and then after they trace their hand, just it swirls back and forth. And doesn't that look cool when it's colored?
Yeah.
Yeah, I thought that was awesome. And then this like kind of self-portrait, Leilani, beautiful. And that is our slideshow.
I already forgot. What's the prompt for next time?
The prompt for next time is to make an umbrella card.
Oh, we just did that.
Yeah, that's our prompt for next time. And then quick reminder, if you would like to have your artwork featured in our show, and also please let us know if you would like to see more art or if the amount we're showing is good, because we're trying to find the right balance between sharing the art but not slowing down the pace too much. But if you would like to share your art, you head over to Facebook. And on Facebook, you'll see this, gotta get to the right side. You'll see this post here. And then if you click on that album, then just click on the prompt that matches. And Science Mom Liza and I are gonna put all of the ones for the rest of the week up so that then you're not having to do it like right the night before. You can even work ahead a bit if you want.
All right.
All right. Now it is time for dun 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 dun. Math Dad.
Whoa. All right. So we're going to answer the question from last time, but before we get there, I'm going to tell you a couple things. So we have this fun paradox by a mathematician named Zeno. So they call this Zeno's paradox. And it was this idea that if I shoot an arrow at a target, then before the arrow can get to the target, it has to go halfway to the target. But then it's still not there. But then before it can get all the way, it still has to go halfway again. But then it still has to go halfway before it can get to the target. And it still has to go halfway. But each time it's going half of a half of a half of a half. And it's got to do that forever and ever. So Zeno said, it's never going to reach the target. Huh. That's kind of a little weird. Huh. So everything he said was true up until, but it's never going to hit the target. What's wrong with that? And so it's kind of this weird idea that things have to happen in a certain way. And there are lots of ways of resolving this paradox. Maybe a paradox isn't even the right word for it because it's not such a big contradiction. But basically you could just say, well, the arrow was going halfway to a target that was beyond the target. And yeah, you can quickly refute it. But it's a really interesting idea, though. Going halfway, then halfway again, halfway again, halfway again. Under that scenario, do you ever reach the goal?
Isn't that doesn't Feynman have this joke about like the mailbox? Like if you go halfway to the mailbox, will you ever get there? And then he's like, no, but you'll get close enough to mail the letter. Isn't that?
There are some good jokes along that line, yeah. So, yeah, if you go halfway each time, often you're not going to get there, but you can probably get close enough to do whatever you are after. So, yeah, they call that Zeno's paradox, and it's going to relate to our immortal hippopotamus because we had a hippopotamus, and let's see, it was traveling 8 kilometers, then it was doing 4 kilometers, and then up next it was 2 kilometers, then 1 kilometer, then 1/2 of a kilometer, and we were trying to figure out how far did this hippo travel. And I'm curious if anybody came up with an answer. I wasn't online at all yesterday to see.
Remember I showed you there was an amazing answer that came to our inbox, and I'm not sure if it was a science kid or math kid, math That's dad, right. Math grandpa, but somebody submitted the exact right answer, and they'd even graphed it out. It was fantastic.
That's true. They plotted it out in the XY plane and showed we're getting closer and closer to a specific line. And so let's see if we can write our partial answers on our way there. Oops. Okay, seeing people say it about 15 and a half. Let's see. So here it's 15 and a half, but what if it keeps going? That's the question. So this is an immortal hippopotamus that's going to keep going forever and ever and ever. And then down at this end, it's going to get so tiny, I can't even draw it. So let's see. We started off with 8, but then after 2 days, we were up to 12. After 3 days, we were up to 14. After 4 days, we were up to 15. And then we were up to 15 and a half. Well, what's going to come after 15 and a half? It'll turn out to be 15 and 3/4. Thank you. And then 15 and 7/8, 15 and 15/16. It's going to get closer and closer and closer to some number, and that number is 16. And this relates to Zeno's paradox because think about Zeno shooting at a target that was 16 units away. At first, it's got to go halfway, which would be the 8 units. Then it's got to do half of that. And then it's got to do half of the remaining, half of the remaining, half of the remaining. And it turns out then we actually have the exact same scenario here, where we're doing 8 plus 4 plus 2 plus 1 plus a half plus a fourth plus an eighth plus a 16th plus a 32nd. And this is going to go on forever and ever. And so what is the answer then to this hippo problem? The answer is 16 kilometers is how far this arrow would travel if this hippo goes forever. Now, you're likely to say, or I'm sure people are thinking about this, well, it's not quite 16 though, because it never reaches 16. And okay, so at any point in time, the hippo will not have reached 16 kilometers, but if it goes forever and ever, the total distance traveled actually will be 16. So think about it this way. It definitely couldn't travel further than 16 because each day it's going halfway to 16. So you can't possibly get past 16. But at the same time, is there some number smaller than 16 that we won't eventually pass, that this hippo won't eventually get past? And no, there's not. So think about it. No matter what number you think of, maybe think of 15.999999999, lots of nines here. Will the hippo eventually pass that distance? Yes, the hippo will eventually pass that distance. My guess is that would only take maybe a few months and it will be past that. So it doesn't matter what number you name, this is an immortal hippo who's going to walk forever, and it will eventually pass that. There is no number less than 16 that the hippo won't pass at some point. And that's why we can say that altogether the hippo walks 16 kilometers. Now, somebody else might say, well, why not just 15.9 repeating? So here I wrote a bunch of nines. I wrote like 9 nines. But what if the nines went forever and ever and ever? So when we have a repeating decimal, we'll often just throw a bar over the top. And so in that case, will the hippo ever pass that guy? And the answer is no. The hippo will never get past this one. But that's because 15.9 repeating is exactly equal to 16. Those two numbers are identical to each other. So that might blow your mind a little bit. Some numbers don't have a unique representation. 16 point all zeros is the same as 15 point all nines.
What? So you're saying there's more than one way to write the same number?
Yeah, there's more than one way to write some numbers. Yep.
And 15.9 repeating forever isn't the same as just rounding up to, like, you're not rounding up to get to 16. It actually is 16.
Yeah, it actually is 16.
All right, that definitely blows my mind.
Okay, so let's do a little detour for a minute then. All right, so maybe I'll simplify this. 0.9 repeating, I'm claiming that that's equal to the number 1. Well, let's see. Why would that be? Well, what is 1/3 plus 1/3 plus 1/3?
You're asking me to solve it right now on live TV?
Yeah. So 1 plus 1 plus 1. So this is actually a really good reminder. So when you're adding fractions, you keep the denominator. And in the numerators, 1 plus 1 plus 1 is 3.
And 3 over 3 is 1.
And 3 divided by 3 is 1. All right. But what if I wrote these out as decimals? I would write 0.3 plus 0.3 plus 0.3. So these are repeating decimals. But it should still equal 1, right? On this right-hand side, it was 1. All right. So 0.3 repeating.
0.6 repeating.
So that's right. That's like writing this number, plus this number, plus this number. Well, when you add those up, because these are just 3's in every column, you're just going to get 0.99999 repeating. And yeah, so that 0.9 repeating is nothing other than 1.
Huh.
And we could come up with an algebraic proof as well, but I don't want to get too fancy or too far beyond. But yep, at any rate, the hippo went exactly 16 kilometers if it walks forever.
Awesome.
All right, now that takes us.
It's right up there.
Thank you. I don't know how I managed to lose this eraser. It just kind of blends in.
Yeah, it's white and it blends in.
It sticks to the board here. It's fancier than any eraser I've ever had.
Well, in the classrooms where you usually teach, there's a drawer on the bottom, and the eraser's always down there. Yeah. Okay. So today I wanted to talk about what we were seeing here. This was something called the geometric series, where each term was a fraction of the number that came before it.
And these show up all the time. Unfortunately, a lot of math classes just never get to this really fun topic. So let's pick a different one. What if I wanted to do 16 plus 4 plus 1 plus 1/4 plus 1/16, on and on forever and ever. So what's happening here? Each number is always going to be 1/4 or 1/4 of the number ahead of it. So this is very similar to the hippo problem, except instead of each number is not a half of what the number that came ahead, it's a fourth of the number that came right ahead. So the question is, what does this infinite series sum to? And
if you add up all of those numbers, what do you get?
Yeah, and by all of them, and we're talking infinitely many of them.
But you can't add for infinity.
Yeah, well, we kind of just did, though, with the hippo, right? We were able to come up with maybe a geometric
That's right. So you come up with
reason.
Like a pattern.
Yeah. There's some number that we're approaching, and by approaching, I mean we can get as close as we would like to that number. We won't actually be able to pass that number typically. But okay, so here is the formula to do this. So I'm just going to write this out. I'm going to write a over 1 minus r. So that 1 minus r is the denominator of the fraction. A is the numerator fraction. So the number a will be the first number. So a equals the first number. And r is the ratio or the fraction that each new number is of the previous number. So this trick will only work when you have a geometric series like this, but it works really well when you have such a geometric series and these terms are getting smaller each time. So in this case, we had, as our very first term, we had a 16. So we would let a be 16, and we're going to let r be, what was our ratio from one term to the next?
I'm dividing by 4 each time.
Yep, so 1/4. Each number is 1/4 of the number that came ahead of it. So in this case, we got 16 plus 4 plus 1, and that added forever and ever. And I'm claiming we can just jump to our final answer, 16 divided by 1 minus that common ratio, which we just said was 1/4. Now, we actually have to be able to do arithmetic with fractions, or we're in trouble at this point. We can't actually evaluate that. Certainly a calculator can if you know how to tell a calculator to do it. But okay, so we had 16 divided by 1 is the same as 4/4 minus 1/4. So we had to get a common denominator so we can add. So that's going to, I'm going to go off the screen here.
Yeah. You want me to try and, I can try and move it down.
No, I'll just migrate over. All right, so that was 16 divided by 4/4 minus 1/4.
3/4
is 3/4. Very good. Okay, and then comes the trick. How do you multiply by how do you divide by a fraction? And the answer is you multiply by the reciprocal of the fraction. So the top, think of that as 16 divided by 1, and then we're going to multiply by 4/3. When you divide by a fraction, you flip the fraction, that's its reciprocal, and then you multiply straight across. All right, 16 times 4 is 64 all over 3. And so 64/3, well, okay, what actually is 64/3? That one would be, put this here, 21, and there's a remainder of 1, so 21 and 1/3. So we were able to add up infinitely many numbers here, and we got our answer.
And I will say, if you're looking at this math and you're thinking like, whoa, Math Dad, you just lost me. This is like super, super advanced Math Dad's favorite math type of math.
My guess is if you're not up to maybe like 6th grade, that this might be a bit much for you.
Yeah, so if you're a younger kid and you're like, what? I don't get it. Think of this as just like kind of like a fun little introduction, because sometimes to learn something new, it really helps to, like, you hear it one time and you're confused. Then you hear it the second time and you're like, And then when you hear it the third or fourth time, then it clicks. And so this might be like a good kind of like first intro for you.
That's true. Now, I mean, and it can look pretty fancy, although all we're really doing is just plugging a few numbers into this fraction formula. And then we get something that involved a fraction that had fractions in it. And we have to know how to simplify this type of thing. So all throughout 4th, 5th, 6th grade, you're starting to learn how to deal with fractions like this. Now we're getting into some tricky arithmetic. And like I said on day number 1, if you don't take the time to learn your multiplication tables and to learn these rules and have a good foundation, then it's going to be very, very difficult to get into this more exciting and fun math.
Arithmetic's like the superpower that lets you do cooler math.
That's right. That's why Science Mama had her tower of math knowledge. And
now I was in the other room looking for the item that is going to be in the what's in the bag riddle. So I actually didn't catch. Did you already introduce this math mystery?
I did not. I'm going to leave that to them.
So if you printed out the notes, we have a math mystery here that will be answered next time.
That's right. I'll write it up because it's easy enough to draw. And yeah, maybe next time I'll even do another example or two of this because it's pretty cool that this formula actually works out. Okay.
While you're writing it, should I ask you the what's in the bag riddles?
Here, this will just take just a sec. So okay. I take a square and I just cut it into fourths. And then I'm going to shade the upper right and the bottom left. And then I'm going to do the same thing. I cut it into fourths. I shade the upper right and the bottom left there. So I'm just working in the upper left corner. Cut it into fourths. Shade and shade, cut it into fourths. Oh no, I just shaded the wrong one.
It's okay.
I had one job.
Everyone makes mistakes, Math Dad. It's okay.
All right, and I'm just gonna keep doing this forever and ever. Well, okay. Eventually, it gets so small that I can't actually physically draw it. But we're looking at some square where this has gone forever and ever and ever. So if you have like an infinite zoom, you just see that this pattern keeps repeating itself. And the challenge question that I have for you today is this question. What fraction or what portion of this big square got shaded in? So we'll be back next time with the answer.
Thanks a lot, Math Dad.
You're welcome.
I have to say, I am really impressed by how many people I saw on social media saying that the hippo walked 15 or 16 miles, which, and 16 is the correct answer, but a lot of people were really close with that answer. And now, are you ready for what is in the bag?
Yeah, let me make sure I can see the comments because I haven't done very well without hints from viewers.
All right, Math Dad wants the comments so that you can have your hints. All right, what's in the bag? So this riddle is on the notes, and if you had the notes, then you had some time to maybe think about this. This one's kind of a tricky one. You measure my life in hours, and I serve you by expiring. That's our first clue. You measure my life in hours, and I serve you by expiring.
Okay.
Second clue.
Milk expires, but I don't measure it in hours.
Milk does expire, but you don't measure it in hours. Lots of food expire. I'm quick when I'm thin and slow when I'm fat. I'm quick when I'm thin and slow when I'm fat. You ready for the third confusing clue?
Most things are quicker when they're slim and slower when they're fat. But I don't.
And the third clue is the wind is my enemy. The wind is my enemy.
Calm, peace. Just what are these again? You measure my life in hours, and I serve you by expiring.
You measure my life in hours, and I serve you by expiring.
Candle.
Yes, it's a candle.
How'd you guys figure that out?
Shout out to, it flew by so fast. You know who you are. Who first guessed candle. Amazing job. So here's how the clues fit. This is pretty cool. And I don't have like one of the tall candles. I just have a little tea candle. So maybe it's not going to be quite as great.
She just had to light a fire, didn't she? Like,
you measure
this room was really stinky yesterday.
It was. So after we finished yesterday, because our steel wool thing, we used smaller pieces. I was like, we need to get 2 big ones so that you can actually see the scales tip. And it smelled so bad we had to open up all the windows in the house because burnt steel wool does not smell good.
But a thin candle
so a
would
thin
burn
candle.
down a lot faster.
Yeah, you measure my life in hours, and I serve you by expiring. I'm quick when I'm thin and slow when I'm fat, because a fatter candle burns slower than a thinner candle. The wind is my enemy. The wind will blow it out. Yeah, pretty cool, right?
Yep.
So that is our what's in the bag joke. And now for our jokes, we have 2 jokes, and one of them was sent in by one of our viewers. So here we have, oh, wrong tab. What do you get when you cross a Labrador and a magician? Labrador and a magician.
Barking hocus pocus. I don't know.
A labracadabrador.
Nice.
And then this joke came from one of our viewers, and I thought it was so fantastic. Where do generals keep their armies?
In their sleevesies?
Yes, you know that one? In their sleevesies. Because your arms go in your sleeves, so your armies go in your sleeveys. I thought that one was fantastic. Where do you keep your armies? In your sleeveys. So thank you very much for passing that on. And if you have a joke you'd like us to share, feel free to send it our way. And now before we go further into some questions, we've had a lot of requests for a song. And before you sing the song that you don't know the words to, I'm going to tell you that so many requests have come in for Let It Go from Frozen. I thought it might be sort of fun, especially because today you gave kind of a hard math lesson. And so our kids that made it through that more challenging math lesson that was really like a stretch for some of them, I think we should reward them by having Math Dad do a little karaoke.
Yeah, do I know the words to Let It Go? I know the chorus.
So if I pull up real quick, because we have Ethernet, so we can do this now because our laptop's with the Ethernet. If I pull up Let It Go karaoke and just play a video, can Math Dad sing Let It Go? That's what we're going to try. Okay.
Anyway. All right.
Awesome. So I have to say, when Frozen first came out, a couple of our kids really, really loved that song, and they sang it non-stop. And when they first started singing it, they were off key quite a bit, and we would be listening to them kind of being like, oh, wow, we're hearing this a lot. But all of that singing really improved their singing, and then they got better and better. And I think I credit that song with why our second daughter really loves to sing, because she sang that a lot. So I'll have to practice. Maybe we can take some requests next time and do a little karaoke song at the end again.
Start losing viewers.
You guys let us know what you think of that. That's what the mute
button is for.
I saw someone in the chat say, "What the heck was that?" That was experimenting. That was experimenting. Good job, Math Dad. We had so many people requesting Let It Go from Frozen 2. I thought, why not try that? Because there are a lot of requests in the chat.
I didn't see a single request. I think you might have made this up.
No, you can check with Science Mom Liza. She'll back me up on this.
I don't know if I trust. It's a conspiracy.
All right. Before we finish, I wanted to take some time for questions. So if you have questions, and I'm going to say, please try to focus these on science and math. So any science and math questions. And I will say, Math Dad, we had a question last time we didn't have time to get to, asking you to explain PEMDAS. And if anyone is thinking, PEMDAS, what in the world is that?
So that's the order of operations. So it has to do with when you have 3 numbers with some operations between them, maybe some addition, some multiplication, you actually have to do the multiplication before the addition. So if I did 2 plus 3 times 7, well, so that's got, if it's written out, then you know that the multiplication, that 3 times 7 happens before you add the 2. So PEMDAS, so we got PEMDAS. So the P is for parentheses, E is for exponents, which means repeated multiplication. You may not know about that yet. But then the M and the D, so multiplication and division, and then addition and subtraction for the AS. So I see somebody writing, please excuse my dear Aunt Sally. That's another acronym for it. And yeah, it's important that you do the operations in the correct order, because you could get all types of answers if you choose to do them in incorrect order.
And then I saw someone pointed out that in the answer sheet, I spelled candle wrong. Instead of a D, I put an O by mistake, and so it says cannoli is the answer. So I will go and update that when we're done. Thanks for catching that. And then I saw a couple questions about the periodic table, about who discovered the periodic table and how do we use it. So I'm going to answer that real quick, and then keep your questions coming. Science Mom Liza and Emily will be forwarding them on to us on our phone, so that if we miss a really good one in the chat, they'll get it to us. So our periodic table here, excuse me. The cool thing about this is that Mendeleev, a scientist who lived in Russia, when he first started putting it together, there were pieces missing. So he noticed that certain elements, like the ones that I drew in the little comic for today's notes, certain elements like sodium and lithium and potassium, they were super reactive, where if you put them in water, then fireballs instantly, they would react with water in a crazy way. And he said, you know what? These are so similar, they should go in order. We should put them in a column. And he started organizing all of the elements like that and realized, hey, when you get over here to element 2, if we wrap around and then you get to element 10, we wrap around, this kind of makes a table. So he started organizing in this way, but there were pieces that were missing. And the cool thing he did was make the prediction that here, where we don't have anything, where, let's say, where fluorine goes, there should be an element there and it should behave like this. And then as scientists started discovering more elements, they realized that this was right, that if you could use the periodic table to predict and find new elements. So that's one way that we use the periodic table, but another way that we use the periodic table is just by helping us have a quick way to identify and understand different elements, because there's a lot of information on this table. And let me bring you a little bit closer to sort of explain some of the cool things that you can find here. So this periodic table, because it is a poster that I ordered online, unfortunately, we kind of have some numbers covered up right here. But let's take a look at, which one should we pick, Matt? Silver. Let's come over here to silver. So silver right here is Ag. This number 47 tells us that that's how many protons we have. And then this big number down here, 107, that tells us how many, on average, like if you get a whole bunch of silver atoms, some of them are going to be one isotope where you have 47 protons, 47 neutrons. Some of them will be another isotope where you'll have 47 protons, but you might have a different number of neutrons.
It would be 60 or 61 probably.
Yes, so when you get up to the heavier elements, you actually end up with more neutrons. If we come up to, let's see if I can come all the way up here to carbon. Here we have carbon. Carbon's a great example. So 6 protons, but you'll notice that the number for how much, this is how much a mole of carbon weighs, how much a block of carbon weighs is 12.01. That's how much each atom weighs on average, because most of our carbon is carbon 12, where we have 6 protons, 6 neutrons, but not all of it. Some of that carbon is carbon 13 or carbon 14. It has extra neutrons, and that's why this number is a bit higher than 12. That was a good question. And
so I've heard of like carbon 14 dating. So that's a different type of carbon?
Yes, so carbon 14 is a different isotope of carbon, and it has 2 extra neutrons in it. But that carbon 14 is pretty stable, but eventually it breaks down. And when it breaks down, it sort of leaves this little signature, and we can tell how long it's been around. So that's how you can look at how much carbon 12 to carbon 14 there is, because carbon 14 is made naturally through radiation from the sun. And you look at the ratio of those two, and you can tell how old something is. So we call that carbon dating. Good question. Do we have any others that have come in?
Why does water feel wet?
Why does water feel wet? This reminds me of a question that you'll often get in middle school science classes, a debate with, is water wet? So that's the debate question. Is water wet? And then oftentimes teachers will have classes argue this back and forth. And it all depends on how you define the term wet. Because if wet means it's touching other water molecules, then any amount of water is going to be wet, because those molecules will be touching other molecules and the water will all be together. But it all depends on how you define the term wet.
All right, why can't carbon dioxide be a liquid?
why can't carbon dioxide be a liquid? Carbon dioxide cannot be a liquid on our planet because we don't have enough pressure. But if you add extra pressure, it can be. So if you put dry ice into a small container, and then you have that container be strong enough that it provides enough pressure, it actually will turn into a liquid. But then, of course, the dangerous thing with that is that if you are not being very careful, you might have that container explode. But on Earth, we have a certain amount of pressure from our atmosphere, and that amount of pressure is not enough to get CO2 to be a liquid. On other planets like Neptune, Saturn, and Jupiter, it is a liquid. Good question.
I'd seen a question. Which comes first?
Hold on, we're going to answer this one real fast. What is Math Dad's favorite operation? So if you had to pick multiplication, division, subtraction, addition, what would you pick?
So those are my only options?
I'd say any operation. You probably know other operations that are not as common.
I mean, I like exponentiation. So.
Exponentiation? Tell them what that is.
So that's when you raise something to a power, you write it as a superscript, like 2 raised to the 3rd power means you're going to repeatedly multiply 2. You're going to do 3 times 2 times 2 times 2, which is?
2 times 2 is 4 times 2 again is 8.
That's right. So 2 to the 3rd power is 8. But what if I did 3 to the 2nd power?
3 times 3 is 9.
That's right. So 2 3s get multiplied, and you'd get 9. That's right. So if I had to pick a favorite operation off the top of my head, I like exponentiation.
Exponentiation. Very nice. Good choice.
So somebody had asked in PEMDAS, so in the order of operations, does multiplication or division come first? And the answer is, doesn't matter. It could have written PEDMAS instead of PEMDAS. It's the multiplication and division, they're actually just the same operation applied to an inverse. And actually the same thing's true with addition and subtraction. As long as you are subtracting the right pieces, respecting the order, because order matters, then addition and subtraction can be done in either order as well.
Very nice. Very nice. We'll answer a couple more. What is my favorite chemical compound? Another great question from Daniel. My favorite chemical compound is water. In fact, I like water so much, I made an entire series of 7 videos all about water and cool chemistry that you can do with water. This is a good question. I'm very confused about the bottom rectangle on the periodic table. It's hard for me to click off because the chat moves so fast. Can you explain it? Yes. So let's look down here, and again, because this poster is made more for it to be an artistic periodic table, they put all this stuff in front of it. But the periodic table, you have this part here, and then there will be this long section down here, the lanthanides and the actinides. And the reason why you have those down there is just to save space, because they actually go right here. Here is where they go. But if we move this out and then put all of these in here, then it makes the table so long that it's kind of hard to fit it on a poster or on a backdrop. So typically these are written out underneath. But see, this is number 56. And then we come down here for 57, 58, 59. And then over here, if we get to hafnium, that's number 72. So right here, this is where all of this would go. But then because it stretches out so far, that's why you see that block on the bottom of the periodic table. That's a good question.
So each row represents a new electron shell level, is that right?
That's a pretty good way to think about it, yes.
Okay.
It's electrons are weird, and it's a little more complicated than that, but yeah, in general, you have fewer electrons at the top, and then as you go down, you're getting bigger and bigger atoms and more layers of electrons. Good question. And what state of matter are bubbles? That's a great question. What state of matter are bubbles? I'd say they are a gas surrounded by a very thin layer of liquid. That's what a bubble is. Gas surrounded by a super thin layer of liquid.
I think of the layer of liquid as the bubble itself. It just happens to have some gas inside of it.
Yeah, I guess it all depends on how you want to define a bubble. But would a bubble exist without the gas inside it?
It would collapse. Yeah.
Yeah. So I think you got to have both. If you, let's see, let me check the phone real quick.
So earlier you were asking for chemical formulas. This question had occurred to me, and I should have asked it. What about something like milk?
Oh, what's the chemical formula of milk? It's very complex. Okay, the chemical formula of milk, you're going to have mostly water, that's H2O, so that part is easy. You're going to have some sugars like lactose. And if any of you are lactose intolerant, Math Dad is lactose intolerant, lactose does not agree with him, then you know that that sugar, and that would be just like there's a ring of carbon and another ring of carbon and they're hooked together. That's what lactose is. So that molecule, we can write out the chemical formula pretty easily. But then you also have fats and proteins, and those are much bigger molecules and much more complex. Most of the protein in milk is casein, and they're these big round proteins, but then you also have whey. Have you ever heard of curds and whey? Or have you ever seen like with muscle drinks, they have like, this much whey in it to give you extra protein? Well, those come from milk. So the whey proteins, and there's several, are different than the casein proteins with like what shapes they have. But those are both really big molecules, and they have carbon, hydrogen, and nitrogen. That's what makes up most of what you have in milk. That's a good question. But yeah, once you start to get into biochemistry, it's like the molecules get really big, really fast, and really complex.
And it sounds like if you just separate the individual components, that you can answer the questions for those a lot easier than maybe it's not even a good question to say what's if I pour all these things together, what's the formula for it?
Yeah, milk is a mixture. It's a very complex mixture of lots of different things. Good question. Ooh, I saw someone ask, what is the chemical formula for plastic? It all depends on the type of plastic. Different plastics have different chemical formulas. And you might notice on the bottom of a container, you will see, let's see, what does this one say? Number 2 in a little triangle, and then underneath it says HDPE. That stands for high density polypropylene, I believe, but I would want to double check myself. So you have basically long chains of carbon that are hooked together to make up plastic, but the way that they are hooked together determines whether it's the type 2 plastic or type 4. And when we melt them down to recycle them, it's important to not mix them together. So that's why you have those little triangles underneath. And in my slime video, if you click on the slime video and then follow through to the Patreon page, I actually have some worksheets that show you the little subunits in each of those plastics. And you can kind of do a little treasure hunt around your house to see how many different types of plastic you can find. Because although glue and plastic seem very different, just in terms of like the basic backbone of what they're made of and the idea of a polymer, they're fairly similar. So there is kind of a connection between slime and plastic. Good question.
That is cool.
All right, we had a couple more questions come in that science.
What gas is in a black light?
Oh, that's a really good question. What gas is in a black light? I'm gonna shout out to Science Mom Krista and say, can you put that one like on our little list of questions to answer so I can look it up and do it justice, because I'm not sure off the top of my head. I have a guess, but I don't know if my guess is right, and I would love to look this one up.
How many elements are in the periodic table?
Currently 118. But I have to say that this last little row here, these heaviest ones, they've only been made in laboratories, and they've only existed for like milliseconds before they break down into, they're radioactive and they decay. So you guys probably have heard of, where's number, I think it's 96, plutonium? Nope, not 96. Maybe.
It's a mystery.
Yeah, there it is, 94. I was so close, you guys. 94, it's like right behind this microscope. Plutonium, is radioactive. And if you have pure plutonium, it's going to be breaking down into a different element. And most of these elements that are heavier, they are radioactive too. And if you have some of it, it's like, look out, because it's not going to be that element for long. It's going to be decaying. And when it decays, it kind of gives off some energy, and radioactive things can be somewhat dangerous. And I forgot, what was the original question?
Just how many?
Oh, how many?
There were.
So it's possible that there could be even more than 118. That's possible that there could be bigger elements, but
I think some of these actually haven't been produced. We just know that if they exist, this is where they would go, and they don't even have good names.
This is kind of outdated. I think all 118 have been named by now.
That's a good question.
And I believe that they've all been produced, but again, and this is the great thing about science and about having the internet, this is something we can fact check. We will have to look it up and see.
What's the smallest of all the atoms?
Smallest of all the atoms? Hydrogen, number 1. Hydrogen is just the most common type of hydrogen that we deal with, is just one proton and one electron. And that is absolutely the smallest atom you can have.
So you should go left to right, but top to bottom and left to right to get from smallest to largest.
Yep, good question. All right.
Is space endless, and is there more pressure in space than on Earth?
Good question. Is space endless? As far as we can tell, no. There does seem to be, because we can tell the universe is expanding. What is outside the universe is a great theoretical question. Who knows? But our universe itself, we can tell, is expanding and getting larger. And is there more pressure in space? No, there is much less pressure in space. So here on Earth, we have a certain amount of pressure and weight because of the air that's around us. When you go into space, you have what's called a vacuum. And that vacuum of emptiness is really kind of crazy when it comes down to the physics of it and how things behave in outer space. There's way less pressure. There's no pressure. These questions are flying by really fast. We'll try and catch just a couple more. And Emily and Liza and Krista, if you can help us out, text us if you see a good one, because it's going really fast.
Is fire an element?
Is fire an element or a part of matter? That's a great question. And now it's gone and I can't. There we go. Hide. Fire is a collection of very hot, small particles that are combusting and breaking down into other particles. And so in the case of the candle, you have carbons that are attached together. And then as that candle burns, those carbons break apart into carbon dioxide. And when they do, they release heat and they release light. And that's what you're seeing. So fire is actually you seeing a chemical reaction, which is really pretty cool.
Yeah, it is.
Let's see.
Yeah. And I think that there's still more to learn about what fire is and some of the theories around it.
We had another question. Can you go outside the universe? I don't know. That's a fantastic question. Oh, can Matt Dad play his violin for us? We will see. Ooh, have I memorized the whole periodic table? Yes, I did memorize the whole periodic table. I can't. It goes too fast and I can't click off after I click. I did memorize the periodic table when I was in middle school. I think I was 13 years old when I memorized the whole periodic table. It was for my science class, and we were given a blank periodic table and we had to write the whole thing on. And I used to know a song that kind of helps you have all the elements. Do I have the entire periodic table memorized now? I do not. If you just gave me a blank one and asked me to fill it out, I think I would maybe get a third of it filled out, is my guess. But I love the periodic table, and I'm happy that I've got it for reference right here.
That's right. So it's 9:59.
It is. So we need to wrap up
our time. So we've had a lot of fun, and the questions just keep coming. I like some of these questions. They're thinking questions, the type of things that will teach you something when you come up with the answer, and that's fun.
Yeah, thank you so much for joining us. I am seeing more requests for Can Math Dad Sing Into the Unknown. I don't know that Math Dad is going to forgive me for making him sing on live YouTube and Facebook today. He's really a good sport to have done that for us. I don't think we'll make singing a regular thing, but if you enjoyed it, let us know, and maybe every once in a while at the end we'll do a little song, and maybe we'll even bust out the violin, because you do play the violin. We'll see.
Look at the time. It's time.
Look at the time. Time to go. Thank you so much for joining us today. We hope that you enjoyed learning, and we're excited to see you again tomorrow with more chemistry and math. Bye.
Take care.